Okay, hello. So my name is Cossairt. Thank you for coming to my talk. Today I'm going to talk to you about hardware and algorithm co-design with event sensors, a couple of projects that we've done in this area at Northwestern. So I'm an associate professor of electrical and computer engineering and computer science at Northwestern University, and I run the computational photography lab at Northwestern. And the work that I'm showing you today is primarily, most of the work is a collaboration between my lab and the Image and Video Processing Lab, IVPL, at Northwestern, that's run by Professor Katsagelos. And before I get started talking about the work, I want to make sure to give acknowledgments to the students who actually did the bulk of the work. So most of the work that I'm going to be presenting today was work that was completed by Nathan Matsuda, who was a PhD student in my lab and is now at Facebook Research Lab, Facebook Reality Labs. Winston Wang, who was a PhD who graduated last year, who's now at Apple. And then Henry Chop and Shrutarshi Banerjee, who are PhD students in the IVPL lab. And I'm also showing a little bit of work from Peng Kang right at the end of the talk. And most of the work that I'm showing today was funded by DARPA, although there's little sprinklings of work from a couple of other agencies as well. So I'll start off by talking about the computational imaging paradigm. And the philosophy here is one of hardware and software co-design. And it starts off with this idea that you can treat your illumination as a way to computationally encode scene brightness information by essentially, you can think of it as being able to program the rays that come from your source that interact with your scene. And then you have a notion of a computational camera that produces different linear combinations of scene points that together produce measurements at each pixel on your computational camera, which then can be represented using this sort of coding equation. And the idea is that your measurements that you make Y are all coded according to your coding function A. And your coding function A is something that you design by choosing the types of computational illumination and computational optics that are part of your system design. And part and parcel of this philosophy is this idea that there is a decoding process that must inherently take place. So there is some software decoding that essentially inverts whatever the forward operator that takes you mapping from your scene parameters X to your coded information Y. And you have to get back to that using some computational decoding. So this is, at its heart, is the philosophy of hardware software co-design. The name of the game is to come up with good A functions that can be implemented realistically using physical devices, and to do it in such a way that we can come up with some decoding software that works in conjunction and is optimized together with whatever our physical constraints is of our optical system. And we've had a lot of success applying this principle to a bunch of different fields. In particular, we have looked at applying this computational imaging paradigm all the way from the nanoscopic scale up to the astronomical scales, working on everything from nanotomography problems to computational microscopy problems, to things that happen at the photographic scale, which is mainly what I'll talk about in this talk, including 3D scanning and high-speed video, but also other applications such as looking at long ranges, trying to image through clouds and fog using remote sensing techniques, and so forth. So I'll just give you a couple examples of some of the successes here. So this is an example of a technique called remote Fourier tychography imaging. And the idea here is that you want to try to image an object at long distance, for instance, a person long distance, and you want to be able to identify their faces. And ultimately, this problem is limited by the size of the aperture of the lenses that you use for your cameras. And it's very difficult to produce very large apertures, but one of the things that you can do is you can introduce illumination. In this case, we're focusing on illumination that is coherent, which is to say that it's coming from laser sources. And you can play around with interesting camera designs. In this case, we're using an array of different camera designs that's very similar to a light field array. And because it's coherent illumination, the images that you capture look very strange. So they look like these speckly patterns. And because the objects are so far away and the apertures are so small for your cameras, the images look basically like garbage. But you can synthesize the images that are captured from each of your individual cameras to produce these super resolution results that pull out details that were basically invisible from each of the individual images that you capture using this computational approach that fuses together information about the physical sensing using our camera array and the problem, and also the coded illumination from our lasers, together developing an algorithm to recover these higher resolution images. That's one example. Another example is the so-called looking around corners or looking through scattering media problem. Another problem that we've looked at where we have a source. In this case, we look at a source with two different wavelengths. It goes through our scattering medium, reflects off of the object that we want to be able to see, but we can't look at it directly. We can only see it through this scattering medium. Scattering medium could be a cloud if you're talking about a large object. It could be tissue if you're talking about a small or biological object. And the idea is that the light that gets through at each of these different wavelengths produces images that, again, look like these speckled patterns. It looks like there's very little information there. But based on knowledge of the source or the illumination coding alone, we can actually just take these images that look like noisy, speckly images. We can combine them together computationally to produce an image that contains information about the latent object in these fields, that is extracted from these fields, the data that we've sensed, produce a computational algorithm that allows us to reconstruct images through the scattering media, even though we're not able to look at it directly. The only thing that we can see are these very noisy looking images right here. So all of this idea is really linked to this notion that we have an imaging pipeline that takes us from our scene through our optics, through whatever computational processing that we are going to perform on the images that we capture to try to extract some form of scene information that's useful to us. The problems that I focused on before are really about just extracting spatial features, but in the very abstract sense, this might get into higher level information, such as trying to understand what's in the scene, to try to track objects in the scene, identify objects, and so forth. And a key component here is this idea that we can link together the optics and the computation and the scene information that we're going to try to reconstruct. And we can try to come up with an end-to-end system design that allows us to do this more efficiently than we could if we were just optimizing these components independently. And this concept is intricately linked to the development of biological visual systems. So there is inherently a link between the types of eyes that exist in nature and the computation that can be performed from the biological organism that has developed that eye, which is always tied back to some important biological imperatives, such as finding food, searching for prey. And so this notion of linking together the sensing and the computation in this joint framework is something that we take a lot of inspiration from biology. And it's one of the reasons why we've started to get interested in particular in event sensing. Okay, and so in particular, this is this illustration here, which I think is probably very familiar to a lot of you guys, gets at the heart of what is so interesting to us about event sensing. And the idea here is that we're showing for the same bandwidth the video frame side by side with the events frames that are produced from an equivalent sensor. And the point is that the event sensing is very sparse, so the amount of information that you actually need to transmit is very small, and which means that you can send motion much faster. And this is something that can be taken advantage of in two very interesting ways. Okay, so we have looked at 3D camera systems using event sensing systems, which I'll go into detail when I talk about the MC3D camera system. And then I'll go into some details about some high-speed video work that we've done, incorporating events together with intensity information as well. So first, let me go into this idea of using event sensors for structured light. So just a brief overview here. So the two large families of 3D sensors The first based on triangulation principles, so those could either be passive methods such as stereo or photogrammetry, where we have two different images taken from two different perspectives that produce two different perspective mappings of a scene. If we have calibrated cameras, we can identify common features from the different images, then we can compute their 3D distance directly in this passive sense. But of course, this sort of technique relies heavily on the amount of texture that you have in a scene, and so to produce dense 3D measurements, usually you control the illumination that you project into the scene, and with some knowledge and calibration of the illumination and the camera geometry, you can recover 3D information densely without having to worry about what the properties of your scene are, if there is texture in it or not. Of course, there's also time-of-flight based 3D sensors. These come in the form of LiDAR, continuous wave, and then also very closely related, essentially still a time-of-flight principle, are the optical interferometry techniques. So I'm not going to focus too much on the time-of-flight techniques. I'm just going to get into how to apply event sensing to this notion of structured illumination. And the concept is pretty darn simple. So the idea is that we have a laser projector that's projecting one point in a scene at a time. And we have some notion of how the point is being scanned across the pixels, J, in our illumination projection space. And then we're going to capture the images of light reflected off of points in the scene with an event camera. The event camera is going to fire one event at a time for each point in the scene that gets mapped to a pixel location I on our event camera. This is just a simplified 1D example here, but it of course extends to 2D. And so the idea here is that if we plot the event position as a function of time, and we have some notion about how to synchronize the event timing together with the timing of the laser projector, then we just look at the difference in the position that the point gets mapped to after doing stereo rectification, and what we get is the disparity. And this disparity, if we have calibrated cameras, if we know the intrinsics of the camera and projector, can be used to recover dense 3D models. And the real interesting thing here is that if we look at the depth information that's captured from this event-based 3D camera, and we compare it to what would be captured with a normal frame-based intensity camera, all of the information can essentially be captured within one frame that would be captured in an event camera, which would only capture one line, or in the most strictest sense, one point at a time. And so what this means is that we can use this event camera together with this very simple illumination coding scheme of just scanning points or lines across the scene to recover 3D information in high speed. But there's another really interesting advantage here, which is that because the event sensors are really looking at changes in brightness, it makes them very robust to a problem that is particularly challenging for computational illumination systems, for structured light systems. And so typically when you build structured light systems, you have this fight between the amount of power that you need to use for your source that you're trying to include your structured illumination, together with whatever ambient light there is in the scene. And there's lots of tricks to get around this, but interestingly, the event sensors provide this very natural mechanism to be able to do this. So what I'm showing you here is an image of a laser scanner that's being projected onto this laser bulb. And so this is an infrared source, so you can't see it, but what's happening is that a laser spot is being moved across the source. It's calibrated together with an event sensor over here that's capturing and looking at this image of this light bulb here. And it's only firing events whenever there's a change in intensity, which means that because the light bulb is not changing intensity, it's only seeing events fired where the laser projected its points. So as a result, you can apply this principle. You can actually scan the light bulb while it's on. And this is one of the really unique things about this form of structured illumination that's combined together with event sensing, is that it's very robust to sources of illumination that are not changing, even if they're very bright. And so that means that it works really well outside. So here's some simple experiments with about the brightest day that we could find outside of our lab at Northwestern. Simple experiment with Nathan moving his hand back and forth in front of the scene so that you can see that as the color turns red, his hand is moving closer to the camera. And you can see that a comparison to the Connect 2 sensor, which is also using this temporal modulation form of rejecting ambient light, but still suffers from a lot of noise in this very bright light conditions, where our motion contrast-based sensor is producing pretty darn good 3D results even in these very bright conditions. Okay, so that was our work on 3D scanning using event sensors, and now I'm going to tell you a little bit about our work in high-speed video. And so for us, this work really started off with an interest in compressed sensing video. And so we have some previous work where we built coded mask systems that were doing spatial temporal coding of images, so that the images that you capture, given some model of the way that the spatial temporal coding is performed using this device, allows you to recover high-speed videos from a single frame. And so these are snapshot video reconstructions of images that are captured using this specialized hardware that essentially has a mask that vibrates back and forth during the camera exposure. We also have some work doing high-speed 3D reconstructions in microscopy, and so these are some examples of some bacteria tumbling around, and dynamic 3D reconstructions that are being allowing us to observe the bacteria in real time in its natural habitat. So this is sort of our motivation why we're interested in high-speed video sensing. And here's some of our initial work with looking at trying to incorporate events together with this problem of recovering high-speed video from intensity frames. So this is work from Winston that was presented in the CVPR workshop in 2019. And the idea here is we assume that we have an event stream together with an intensity frame. We bin together the events into a set of event frames. Together, these event frames and this intensity frames, we form a model of how a high-speed video maps to a single frame and a set of event frames. And then we perform an optimization problem where we try to recover the high-speed video frame by back-propagating information both from the intensity frames that we've captured together with the events as well. And then this result gives us an approximate solution using only a physical model without any sort of priors on the reconstruction process. And then we feed this through a residual learning network, which essentially is trained to learn the difference between the reconstruction that you get using only your physical model and the errors that you get that can be learned to be corrected from a data set of event videos, pairs. So this was our first work looking at this idea of combining together information from both events and intensity frames. Here's some of the preliminary works from that showing that, here's this nice comparison to previous work where you get some artifacts around the motion of the leg of this acrobat here that go away when you use our event intensity fusion and refinement network. Okay. So that was some of the first work that we did, and then this is some follow-up work that was again led by Winston Wang. Published in CVPR last year, and then also coming out in a journal sometime soon. And so this is this notion of guided event filtering. And so the idea is that we have some imaging device which can again capture events and intensity frames. So we have some set of events, so we have an intensity frame, and then we have some notion of filtering the events based on a special process that I'll go through in a second, based on information about the intensity frame, such that what we get out is an event frame that has much higher fidelity than we would have gotten if we had just bin together the events directly and ignored the information from the intensity frame itself. And I'll go through a little bit more detail about how this works and then why it's useful. So this is the main idea here, is that we have some events here, and suppose that we have some a patch of intensity that has some constancy in brightness in terms of time, but it has some flow. This is going to fire off some series of events based on the flow motion of this patch of intensity in our scene. And so the idea here is that if we had some notion of what that motion was, and then we projected the events back along that line, we would get some histogram of events that were bin together, essentially producing an event frame that has really good contrast. And so this is really the idea here, is that we can search for different different sets of local motion that after we project our events across this flow direction in the event volume, we get an intensity pattern that has the maximum contrast. When we do that, we know that we've identified the flow direction, and so we can use this to compensate for the motion that we get in our event frames. So here's an example here where we have an event frame paired together with an intensity frame coming from a Davis sensor. And this, if we just average together the events, if we just bin the events, we get something without paying attention to what the motion was of each of the objects in the scene. What we get are edges that are moving fast produce really thick lines. Edges that are moving slow produce thinner lines. But after we do the motion compensation, this essentially produces much thinner lines because we've now projected the event volume along the direction of shear in the event space, in the time event space. And then so now the idea is that we have two pieces of information that are very useful, and they're in essentially the same coordinate system now, the spatial coordinate system. We can look at the gradients now of the spatial gradients of our intensity frame. And now that we've performed motion compensation, we have our event frame that has been motion compensated. And we know that these two should be very similar now because we've removed the effect of motion. So all of the events that have fired together when we bin them together should tell us something very clearly about the great spatial gradients that we have in the scene. And so what we can do is we can use our intensity image to help improve the quality of our event frame that is produced after motion compensation. And it turns out that this method works really well. So we use this mechanism called guided filtering. And it allows us to go from an event frame that looks, relatively noisy, relatively low resolution, to something that has, much finer edges, looks much higher resolution, also looks like the spatial gradients are much more consistent with the intensity frames that are captured as well. Here's another example of this duck scene where you can see really nice fine detail edges that look very consistent, again, with what you can imagine the gradients of the intensity frames that you're seeing as well. So why is this useful? So for one of the reasons it's useful is for that same application we were talking about before, where if you have a blurry image and a set of events, you can use it to recover high-speed video. And so here's a comparison with some prior work showing that, especially in regions of very little motion, you get much better results. And you also get a little bit better results for regions where you have large amounts of motion as well. Here's an example showing the benefit of using the guided event filtering for high dynamic range. And here's a nice application which is showing that if you just take the binned event frames and you try to do tracking on it using an off-the-shelf algorithm or previously published algorithm, you really fail with the tracking result, whereas if you apply this guided event filtering to produce event frames that are have much higher fidelity and are also enhanced by the intensity frames that you capture, you can get really nice smooth tracking results. So the last thing that I want to show you is just to give you a taste that the next thing that we're sort of interested in looking at are spiking neural network models, and in particular one of the things that we've started to look at is hybrid conventional neural network or analog neural network and spiking neural network models. Because we think this could be interesting to look at in terms of developing new sensing architectures that are co-designed together with computer vision algorithms. So here's a simple example where we use an ANN module that is specifically trained to take in images that are noisy, so our sensor is very noisy, and then feed out information that is analog processed. So everything on the left-hand side here is analog, and then we have a neural coding layer that produces our analog values into spikes that are fed through an SNN to produce the simple task of MNIST digit classification. But the interesting thing here is that if you look at the difference between just the SNN algorithm by itself versus the hybrid algorithm as a function of increasing noise, what happens is something that is relatively intuitive, which is that the analog filters do a good job denoising the images that were very noisy, such that the SNN can do a better job after the spikes are generated, after the analog filtering process has completed. So these are just preliminary results, but it's an interesting direction that we're looking at moving in the future. So in summary, I hope I've convinced you that there's some really interesting opportunities for joint hardware and software design, this computational imaging paradigm, both in 3D imaging and high-speed camera design. I think that using this bio-inspired notions that are inherent in the event sensing has some very interesting opportunities for increasing task-specific performance with low power and high bandwidth. And I'm also really interested in this new direction of using SNNs to produce better hardware and software optimized designs. So with that, thank you very much for attending my talk, and I hope you enjoyed it. And any questions, I'm happy to take now.